This is probably something new to a lot of us. So in 3 omega, we have a heater. We are injecting an AC current into this heater. We inject an AC current to this heater. The AC current is IT equals I naught times sine omega t. So this is sine wave. This is your AC current that you inject into the resistor. Then, since this AC current is going to induce Joule heating, you will see your Joule heating equals I squared, times R. And you plug this in, you will see your Joule heating has a 2 omega term. It has an AC component that, that changes at a frequency of 2 omega. Then Joule heating in turn will change your resistance. So your RT will also have a 2 omega term. So when you try to measure the voltage across this heater, VT is equals I times R. So you plug I, you plus R into the equation, you are going to get a 3 omega term. This is called V3 omega. So this is a voltage that, varies at the frequency of 3 omega. So that's why it's called a 3 omega method. So again, you inject a current, an AC current into the heater, then you monitor the voltage across the heater. That voltage, changes at the frequency of 3 omega. Why is 3 omega useful? This is the formula of your 3 omega. You see there's a 3 omega turn, and also there's a phase delay. So if you look at this, you will see your V3 omega comprises two components, in phase and out of phase. In phase means your temperature oscillation that is in sync with the sine wave, the sine current input. So it's related to thermal conductivity because the in phase component tells you how efficiently heat can conduct through the sample, resulting in immediate temperature changes. So in phase means immediate temperature change. That's related to thermal conductivity. Then there's also an out of phase term that tells you temperature oscillation that lags behind the current input. So it's related to thermal diffusivity because the out of phase term tells you the ability of the material to store and then release heat over time. So that's more about thermal diffusivity. So we can use the in-phase term to measure our thermal conductivity. So, and the equation here tells you your thermal conductivity is proportional to a slope. What is this slope? This slope is you change your measurement frequency, you change your frequency, then you monitor your V3 omega. You measure your V3 omega at different frequencies, then you get a curve. Then in this equation, we're looking at the slope of this curve. The slope of this curve tells you about thermal conductivity. Okay, in 3 omega method, we change our measurement frequency and we monitor our V3 omega. That tells you about thermal conductivity. And the out of phase term is more related to thermal diffusivity, and it's not as sensitive as the in phase term in terms of measuring thermal conductivity. So just a very high level introduction. Questions? Yeah, it's a lot of math here, but we just need to have a high level introduction, understanding what this thing is doing. So a little comparison here. So we have TPS, we have 3 omega, and we will see, TPS is a DC method, and it hits the sample and measures the thermal response of the sample. It measures how temperature increases. So since it is a DC method and it measures response over time, so during this process, heat is going to diffuse. The longer you measure, then the further your heat diffuses. So the measurement depth is time dependent. It is proportional to square root of alpha t. So your measurement depth increases over time. So TPS is suitable for measuring bulk materials. So the typical, measurement depth is a 0.05 to 6 millimeters. So it's suitable for bulk materials. But for 3 omega, its measurement depth is frequency dependent. It's defined by frequency. So H equals square root of alpha over 2 omega. So you can change your measurement frequency to measure at different depths. So at 1000 hertz, its measurement depth is only 3 micrometers. At 0.1 hertz, it's about 300 micrometers. So 3 omega is very suitable for measuring very shallow, very thin films. And you can precisely control your measurement depth by changing your frequency. By changing your frequency, you can measure at different depths. So that's good for measuring multi-layer structures. And TPS has limitations. It's a DC method. It's sensitive to DC artifacts such as thermoelectric effect. It's also sensitive to radiative and convective heat loss. And it cannot precisely control measurement depth because that increases over time. And 3 omega, has its limitations. It's limited to high thermal conductivity materials because the measurement depth is, proportional square root of, thermal diffusivity. If alpha is too low, your measurement depth will be too shallow, and that wouldn't be very useful. And 3 omega requires an AC method, so that requires more complicated, electronics. So it's a limitation for wearables. Just to show you, an application of the 3 omega method. So we first place the device on the skin. We measure its thermal conductivity. Then we just slap the skin. It becomes red, and we put a sensor there. You will see after slapping, its thermal conductivity increases. Before slap is about 0.25, after slap is about 0.33. Because, when you slap the skin, there will be, blood flow into the skin. That increases your thermal conductivity. We can also use, 3 omega or even TPS to measure hydration. This is just a, demonstration that, you hydrate your skin to different degrees. So this is arbitrary units. So 70 means high hydration, 30 means low hydration. You will see with high hydration, your thermal conductivity decreases. With high hydration, your thermal conductivity increases. Okay, this is about thermal conductivity. All right. So the last part is thermal sensing or anisotropic flows in the body. So this is a pretty